hydrogen chloride gas, not hydrogen chloride acid, and not hydrochloric acid. And you can see as a function of temperature what different types of compounds, what, well, they still like to think of pH, log of partial pressure of oxygen. And so you can look and see what would happen to something like those turbine blades that I passed around. And they have things in here for sulfur. Okay, here's some Fourier diagrams for iron and sulfur. And these things can get really messy. After all, if you've been doing the same calculations for 40 years, you start having to try to make things more complex, right? That's what professors do. But to give you an idea about those turbine blades I passed around, would you like to be flying with that plane? So if you look at the sulfidation, the hot corrosion, and this is just giving you some idea of some things. Fourier explains the thermodynamics of corrosion, but the real problem in corrosion is trying to understand the kinetics, how fast it occurs. And this is for the high temperature corrosion of an overlay coating versus temperature for a nickel, chrome, aluminum yttrium. We call it a nitrolay alloy. So a lot of your turbine blades that are in jet engines will have this corrosion resistant coating on the surface of the turbine blade because it's better than just straight nickel. It's nickel, chrome, aluminum, and yttrium. Well, it turns out below 800 degrees centigrade, you don't have a problem because the kinetics are too slow. Above 1,000 degrees, you don't condense out your sulfur compounds, but in between you have hot corrosion. And notice here, this goes from 0 to 100 and then up to 200. So really this peak is about twice as tall, okay? You have a huge increase, about a factor of 200 increase in the corrosion rate over a very narrow range, where kinetics are too slow for the diffusion at low temperatures, and all your gaseous products are vaporizing away, they're not condensing. There's this one condensing region. Now, this is the type of corrosion that occurred on those turbine blades. What you need to understand is when you start that engine, it starts out cold and it has to go through this region, but you don't want it to stay in this region very long. And basically 900 degrees centigrade is about 1650 Fahrenheit, and that's sort of what you might get with some of the takeoff power in this particular part of the engine. And so we think that what was happening, this was a number of years ago, 6 or 7 or 8, whatever, as I remember, that the Mexicans weren't going down to the end of the runway and running their engines and preheating the engine for 10 or 15 minutes, okay? They figured, well, let's not waste all that gas on the runway getting things up to temperature. Let's just turn on the engine and take off. And what happened is, when you take off, you stay in this region for 5 or 10 minutes, okay? As it's heating, you're now doing your preheating up in the air, okay? At power, full power, rather than coasting at a lower power. And we think that's why they sulfidized so quickly, okay? But, you know, just to show you what can come out of an operating engine. Okay, pretty amazing, isn't it? And it wouldn't have been much longer before some of those started flying through the engine, taking out the engine. Which is another thing. How often does an engine fail? Once? Once. That's for a single engine. I was actually thinking of a statistical number. If you go look, and if you go up to General Electric aircraft engines, they will tell you that it has like a 0.6% probability per hour of failure. Well, that means that you're going to get a failure about 1 every 300 or 400 hours, or 1 every 300 or 250 hours, 250 to 300 hours. How many people have flown 250 hours? Yeah, okay, some of you have. I've probably flown several thousand hours. They don't usually tell you when they have to shut down one of the engines, do they? Okay? But they do. In flight. You hope it doesn't occur on takeoff. That's the worst time to lose an engine. it doesn't really matter too much on landing. You need power for takeoff. You don't need power for cruising. And in fact, the 747s have 4 engines. How many engines on a 777? 2. Why? It was a big deal when they came out with the 777 15 or 20 years ago to get the FAA to certify it for flight over the Atlantic. It used to be if you're going to be more than 2 hours from land, you had to have 4 engines on a commercial big jet. Okay? Because there was a certain, back in the old days, the probability wasn't 99.6, it was more like 98 point something. And you start doing the math on this, and there's a certain probability you could lose more than 1 engine if you're more than 2 hours from land. Okay, but the reliability has been going up. But even so, those of you that fly a lot, you've been on a number of planes that statistically they've shut down an engine because they didn't bother to tell you. Okay. So, just so you know. But you can land on 1 engine if you know how to fly. Okay. What we're going to go over, actually probably not tomorrow, maybe it will, I don't know if I'm going to, maybe it'll probably be on Wednesday, but I'm going to start going through, these are Tom Eager's 9 principles of corrosion. Okay, oops, that doesn't work very well, but we're not going to spend a lot of time on that now, because we've only got a couple of minutes. But recognizing that you are going to be engineering managers in the future. I'm not trying to teach a corrosion course where you learn everything there is to know about corrosion. I guess we're going to pass this around. Here's your 9 principles of corrosion. Hope you don't have to take notes. But you need to know what type of questions to ask those people who are working for you. There's no way in a short little course, 6-week course, that we can tell you everything you need to know about corrosion. Because corrosion is worse than welding in terms of you tell someone a certain rule and then you have to violate the rule later because the circumstances change. Okay? In corrosion, circumstances change all the time. Okay? You can actually draw a diagram. They often draw a diagram for corrosion with 3 circles, a Venn diagram. And this originally was for stress corrosion cracking or hydrogen embrittlement or something like that. And you have to have a stress for stress corrosion cracking. You have to have a material that's susceptible. And you have to have a corrosion. In a Venn diagram, if you remember from math, you can increase or decrease the size of these circles. And the corrosion, the big problem occurs right in here where all 3 of these come together to create the environment for the environmental degradation of the material. It means it rotted, okay? And it fell apart. And tomorrow I will pass this around. It's too delicate to go around right now, but this came out of a hot dog cooker over in Everett, Massachusetts. But this is, it's flaking off as we do it here. This is where they make Fenway Franks. And the hot dog cooker is a lot bigger than this room. It's a big steam tunnel made out of stainless steel. Taller than you or me. Not quite the size of a single car garage. It's a tunnel where they just take all these hot dogs and they got to cook them, right, in steam. And it's supposed to be made out of 316 stainless steel. And it was made out of 316 stainless steel, but over time they had to replace some parts or they put some new baffles in. And all of a sudden, within a few weeks, stuff was cracking and falling apart. I mean, the stuff is, if you look at it sideways, it's bent from all the cracking, okay? And they brought me in and said, why is our cooker falling apart? And I said, I don't know. So I took it back to the lab. They let me have these pieces. And I took it back to the lab and we put it in the scanning electron microscope. And we found the 316 stainless steel was not 316 stainless steel, it was 304 stainless steel. And what's the difference between the 2 of them? has 2% molybdenum. What's the environment? It's a hot chloride steam. It's a lot of sulfur in hot dogs. Okay? Hot, oxidizing chloride. This probably would have dissolved gold over time. Could have made this thing out of gold, and it probably would have rotted your hot dog cooker. But it turns out, the spec was to make the parts out of 304 stainless steel, which is, we're going to learn, is the garden variety stainless steel. But they were supposed to make, they were supposed to make it out of 316, and they made it out of 304. This is the most dramatic case I've ever seen of where you should have used 316 and used 304. So the wrong material can make a big difference, just like I told you about, that destroyer going into the Gulf War, and they lost their 3,000 psi steam line because of stress corrosion cracking, because it was the wrong alloy. So these are two stories of they used the wrong material. In other cases, I'll tell you stories about where the stress was wrong. Okay, in other cases where they had a corrodant that was a lot worse than they expected. So any one of those three things, and these are some of the things that we'll talk about, some of those principles and what happens in general. And a lot of it's going to be sort of empirical stories, but the stories are sort of fun. I mean, now you know how to cook hot dogs, right? You have a 316 stainless steel pan. No. You have to boil in water. Okay, we'll see you tomorrow, 11:30.